Okay, in this video I will explain equation of simple pendulum. Okay, simple pendulum model. You can read more details about this simple pendulum model in my handout of Unit 2, handout number 6. There if you read this handout, you have all the details of this model. Here I will explain briefly about how it works. So we will assume that we have this fixed support. This is fixed. And on this support, we will have the pendulum, which in fact is just this is a rod, some rod, and the length of this rod is known. So this length is L, and the mass is concentrated here at the end. So we will assume that the rod is massless, doesn't have any mass, and the mass is only here. Okay, then important variable here for us would be this angle. Okay, the angle of the rod with respect to vertical axis here. I will assume that this angle is theta. Okay, this angle theta I will assume positive to the right, counterclockwise. Okay, so it's very simple. We will assume that the only force that is acting on this mass would be the mg. So the weight of this mass here. It means that we don't consider any friction here or on the mass, nothing. The only force will be this mg here. Okay, so in these conditions, let's try to write the free body diagram. Okay, for this system. So assume that we have m here, and this is positive direction of theta. So the first force which will be opposing this motion of theta is the inertia, the own inertia of mass that we have seen many times. So it will be j d square theta dt square. Okay, this is the force, and the other torque that it will be opposing the motion of m will be, I will denote this torque T, that is as a result that we have this force, the weight applied on this m here. So you have this T here. So it means that our differential equation is very easy. G d square dt square plus T equals 0. Okay, so this is the differential equation for this, but here we don't know what is this torque T. Let's try to find out what is this torque T. The other thing is this J here. Usually this moment of inertia we assume that is constant, and we know, but in this case we can say that because this is very simple, here in this case we say that J will be m, the only mass here, times this distance L square here, because this is the distance to this point, from this m, from this square. Okay, that's fine. So the other is what happened with this torque here. To determine this torque, we need to project this force here on this axis, okay, on this direction that is perpendicular to this direction, to the road. So in fact what we need is this projection of this force here. This is very simple. You can see that if we have theta here, so this angle we will find again here, so this is also theta, and then this projection here is only mg, okay, sine theta, and that will be this projection here. So it means that finally our torque will be mg sine theta into L, L being this, the distance between this point and this, the length of the rod. So our differential equation can be written J d square theta dt square plus mgl sin theta equals 0, and this m here, this j here is ml square. It means that this m and this m will cancel, and then this square here will cancel with this one, and at the end you can write this beautiful differential equation plus g upon L sine theta equals 0. So this is the differential equation describing the motion of my simple pendulum. Be careful, because even if this is very simple, this is a non-linear differential equation. So you cannot apply Laplace transform on this differential equation to try to solve this. So, okay, you should first try to linearize this, and then you can apply the Laplace transform on this. Okay, so this is it. This is the explanation of simple pendulum.